All right. Uh, Good morning, everyone. I'm Anudeep Midam. I'm a research engineer at Idaho National Laboratory, and my colleague Manoj Sundararajan has worked on it, and we had some other interns who worked on it, but I've not mentioned the name yet. And we have partnered with Idaho Falls Power, and I will be presenting a use case on telecommunications where we would be doing hardware in the loop simulation and the transmission, distribution, and communication co-simulation. Okay, so the objective in this particular use case is to perform real-time co-simulation of all the three domains, that is transmission, distribution, and communication using the Helix platform. And as a uh, introduction, real time, when I'm referring to the real time over here, I'm referring to the clock time and not the computer time, where whenever we do any kind of simulation, it is the computer clock time where if we simulate for 1 second or 1 minute, it would take hardly milliseconds. But over here, when I'm doing the real time co-simulation, it is the clock time. And if I do a fault for either 5 seconds, then it would take the whole of 5 seconds to do the whole simulation and then get it across. So whenever we are doing any real-time co-simulation, there are several challenges associated with it. One of them is making sure the timing is correct between two different domains, and this is where Helix platform plays a crucial role in helping in modeling and running these simulations uh, coordinatedly. So for this particular use case, I have modeled a transmission system in Opalati. We are using a standard IEEE 39 bus system. We have modified it in such a way that it is able to be connected to our distribution system, for which I'll be modeling it in the RTDS. And we have modeled Idaho Falls power distribution system. We have selected some of the a part of the distribution system of the Idaho Falls power system, and we have modeled it. And the communication would be through NS3, that is a network simulator 3, that is another tool that we have used. And we would be performing the co-simulation as well as doing hardware in the loop simulation. And one of the main objective is to see that if we introduce, say, a fault in the transmission side, how does it impact the distribution side and any of the DERs associated with it. Uh, and also if there is any kind of communication fault or a delay, uh, and what is the impact of that. And from- so this is a okay, let me go back to the previous. So the one you see on the right hand side, so we have the transmission system over here, which is the Opal RT, and we have the distribution system, which is through the RTDS system, and the NS3 is over here, the communication layer. And this is a co-simulation implementation where we have the Opal RT, and in the first case, that is part A, we have the NS3 as a communication layer, and the control signals are sent through Helix and received at the RTDS through the NS3. And we also would like to see if Helix also has a communication layer. So we wanted to see if Helix can mm, Helix can replace NS3 as such. So you can reduce one of the domains in a way. So for that, we will be directly sending the control signals from Opal-RT to RTDS through the Helix layer over here. And this is a one of the initial results that we got it. So we did the TDC co-simulation where we passed some of the control signals from Opal RT to RTDS. And in the first case on your left hand side, you can see that the time taken is around 160 microsecond, and this is without any kind of delay. And on the right hand side, you will see a after we put in a 20 millisecond delay, we see the total time is 20.16 milliseconds. What are the highlights of this Helix? It is basically to show that Helix is a vendor-neutral framework, and it is able to co-simulate even proprietary tools like RSCAD. So one of the challenges is, let's say you have an Opal RT, you have the Simulink interface, so it's easier for us to uh, integrate Helix with Simulink, but in the case of RSCAD, it is a proprietary tool from RTDS. So it's the number of ways by which you can integrate Helix with RSCAD becomes challenging, and also it's not as straightforward. So this took a lot of effort and some of the help from other national labs as well. And we are been closely working with the real time uh, component of this Helix with the development team to ensure that with the current time step, whatever we were looking at, we will try to reduce it further from say 500 microseconds to around 50 microseconds in the future. And in the future, we would like to see if we can perform these HL simulations using some of the other DRs like microgrid and even some of the loads like electric vehicle or electrolyzer. And we are yet to finish the co-simulation of hardware in the loop simulation, and that will be done in next few weeks. That's it from my side. Uh, Happy to answer any questions.
Yeah, we got about 5 minutes for questions. I see Jing's got her hands up.
Hello, this is Jin Wang from Unreal. Thanks sharing your work with us. I have a couple of questions. First, you said you have the uh, OPRT, you use OPRT to simulate the transmission system. So what
Yes.
type of OPRT tool? You know, you have ephasing, emegacin, and hypersyn. I'm wondering which one you use.
We use the eMegaSim for this, and
Emegacin for
yeah.
transmission system.
Yeah, so
Really?
we were looking at
I,
all the three different systems. But the main focus was on the standard. Oh, let me confirm again. Was it Emega or is it the Hyper? I will have to check back again. Sorry.
uh,
That
uh,
is. Oh yeah, sorry
yeah.
about that. I will have to check back. So one of my partner, one of our uh, a partner in this project. So he did the Opalati implementation. So it should be, I think it should be the regular ePhaser sim, right? Yeah.
No,
I
if it's
am
a thing, you don't do that as well. Why I'm
okay.
asking, because I'm facing the same, I need to do the same thing as you do,
Okay.
simulate a transmission system in OPRT. If phasor thing doesn't do it, because it's phasor domain simulation and it doesn't do transpose, and the Emega thing doesn't do that either. So in the end, we have to do hypersync. Hypersync has that.
Okay.
Just,
Yeah. Maybe then
yeah.
you're right. I'm sorry about that. Yeah.
Yeah, so
Thank you.
if you want to use OPRT for transmission simulation, hypersync usually is the choice.
Thank
Another question I have is, you showed two options, A and B. A is using the AS3. AS3 is usually used
Yeah.
for the communication testing, and
Yeah.
B you replace, you take out the AS3 directly using Helix. I'm
Right.
wondering why you need to do that. Um,
So this is more to show the capability of Helix, where you don't have to. So by using NS3, you're adding another component, right, as a communication layer. So there will be some
but
kind
this
of
is
challenges.
realistic. In reality, if you see the grid automation, if you will send the control signal from the transmission EMS to distribution DSO, the
Of course,
gateways, enterprise network communication protocol, there's a lot of delays there. So
of course.
that's why
Oh
when I
no.
look at
So
the diagram, I'm a little bit not sure if that is realistic. The
no,
structure you have, yeah.
we are not removing the communication layer as such. The communication layer is being replaced by Helix, where Helix itself has inbuilt components of adding a delay or a packet loss. So that is what we were looking at. It is still I'm
And
still
what sort of control
showing the
signal you
delay.
use?
Sorry.
Uh, you have all party, you send the control signals to the distribution system in RTDS. What kind of control signals? How
Uh,
often do
so
you
uh,
send the control signal?
so we developed a controller within the Opalati system, and we are basically whenever there is a fault, we are looking at the voltages and currents, and based on that, we send a control signal. It would be a basic breaker switch or a reference signal where it sends to the distribution system and says you have to open this particular breaker switch such that you're not connected to the transmission system and you're saving the DERs, protecting the DERs from the grid.
I see. So that's like a freezer, the isolation of the food. So it's
That's right.
really time critical signal. So the delay is very, very crucial. We need to
Right.
minimize the delay. But if you
That's right.
have other control signals, let's say the EMS in the transmission system need the DSS distribution system do some grid service. Let's say frequency response or
Yeah.
virtual power plant, then this is another story. So it's good to it is important to tell us what kind of control signal you are sending, if it's time critical or non-time critical. Yeah, that's my
It is.
suggestion.
Yeah. Thank you. Appreciate that. Yeah. It is time critical is what we are looking at right now.
Yeah, thank you. Yeah.
Thank you. Yeah. Any other questions? All right. Thank you, everyone.
All right.